next lesson starts the fourth topic in Module 1 of Engage New York. In this topic, we're talking about congruence criteria, or other ways to show that two triangles are congruent using sides and angles instead of being limited to rigid motions. In this lesson, we'll talk specifically about the SAS, or the side angle side congruence criteria. In this lesson, we will focus on 3 CCRSM standards. The first is establishing the SAS congruence criteria. We'll then prove some theorems, including the base angles of isosceles triangles are congruent, and proving that points on a perpendicular bisector of a line segment are exactly those equidistant from the line segment's endpoints. Let's get started. For lesson 22 in Engage New York, it starts off with an opening exercise to think about, is it possible to know whether there's a rigid motion that takes one triangle to another without actually showing the particular rigid motion? And if you think about that, I'm hoping that you come to the conclusion of yes, it is possible to see two triangles or two shapes and say, even though I don't know what rigid motion would take, I know based on the information there that those two must be congruent. So for example, if you have two triangles that you know all 3 sides and all 3 angles are congruent, even without saying the rigid motion, you know that they must be congruent to each other based on all the sides and all the angles being congruent. Down here we're given the side angle side triangle congruence criteria. And I'm going to explain this using this picture down here. So we have 2 sides that are congruent and 2 other sides that are congruent and the angle in between them. So we have a side and an angle and a side and an angle and a side. And so we call it the SAS triangle congruence criteria because the angle is in between the sides just like the A is in between the S's. Now, we can't just assume that's true, that if you have this criteria that they'll be congruent. We have to prove that it's true. And down here, it starts a proof of proving that these 2 triangles are congruent regardless of how long the sides are and regardless of what the angle is, that going through a proof that given this information of these sides and the angle in between them, that we can create a series of rigid motions that'll show that these 2 must always be congruent, and we'll do this generally for any lengths and any angles. Let's start on this proof. Oh, before I do the proof, let me also point out that this is one of our standards, so go ahead and put a standard star with this proof and be familiar with this proof because you may need to answer questions about it or recreate the ideas in this proof because it is one of our standards. Okay, we start off by using a translation. So we translate using this distance and direction, that vector, so that A prime maps on, is translated to A. Okay, and a translation is a rigid motion. And we get a picture like this. All right, because A prime mapped onto A using a translation. All right, and then what we do is we do a rotation. We rotate C double prime to C using a rotation, which is a rigid motion. And then we have a picture like this, and then we simply reflect the triangle on the right over line AC and shows that they must be congruent because they map onto each other. And so that is a sequence of rigid motion that takes A prime, B prime, C prime to ABC with the use of just 3 criteria from each triangle. Now again, this proof was done generally with any lengths and any angle as long as the angle is in between the 2 sides. And so we can use this in a proof regardless of the lengths and the angles because we've just proved it generally. And that is the proof of the side angle side triangle congruence criteria. Now, I want to use the idea of the side angle side congruence criteria for a few problems. The first is down here, number 2. Given angle LNM is equal to the measure of angle LNO, that's drawn for you right here, is equal to LNO, and MN is equal to ON, do triangle LMN and triangle LNO meet the SAS criteria? Well, something happens here that we've not talked about yet, but will become very useful for us over in this topic. And that is something called the reflexive property of congruence, which means that any side or any angle is congruent to itself, which hopefully makes sense that any side, any segment will be the same length as itself, and any angle will be the same angle as itself. But this reflexive property will be very useful for us because segment Ln is congruent to itself because of the reflexive property of congruence. So with that idea in mind, our goal is to use the side angle side triangle congruence criteria to prove that triangle LNM must be congruent to triangle LNO. Now in a proof, we always start with the given. So we'll start off with the measure of angle LNM is equal to the measure of angle LNO, and MN is equal to ON because it's given. Next, we'll say segment LN, length Ln is equal to length Ln by the reflexive property of congruence. Now, hopefully you notice that we have a side and an angle and a side, and a side and an angle and a side in both triangles that are congruent. We can use the side angle side triangle congruence criteria to say that these triangles are congruent. And that's the whole proof. So let's go down to another problem that uses the side angle side triangle congruence criteria, but this one is going to be in lesson 23 about the base angles of isosceles triangles. At the top of the page, it gives you a proof using transformations, but the proof I want to focus on is the one that uses side angle side. In this proof, we are given isosceles triangle ABC with AB equal to AC, and that's drawn for us in the diagram. And our goal is to prove that angle B must be congruent to angle C. And those are the base angles of this isosceles triangle. Now right here, they give us a hint to use the angle bisector of angle A. Now hopefully you see in right there, we have a left triangle and a right triangle, kind of cutting that isosceles triangle in half. And our goal will be to prove that those two triangles will be congruent using the side angle side congruence criteria. And then if those triangles are congruent, then all the corresponding sides and all the corresponding angles must be congruent. Specifically, angle B must be congruent to angle C because they are corresponding angles. That's kind of broad picture for this proof. Let's get started. We always begin a proof with the given. I will next use the hint and draw in the angle bisector AD. Because it's the angle bisector, I know that angle BAD, this angle, must be congruent to angle CAD by the definition of angle bisector. And that's drawn for us in the diagram. And now we'll use the reflexive property because AD is congruent to itself by the reflexive property, and that gives us the side angle side that we need for this criteria. And now that these two triangles are congruent, I know that angle B must be congruent to angle C because they're corresponding angles. And that is the whole proof. Now, before I forget, please put a standard star next to this proof, as that's one of our standards, is to prove that in an isosceles triangle, the base angles must be congruent. The next problem I want to do, and this is the last problem we're going to do, is I'm going to change this picture to meet one of our standards. So this is not the problem we're going to do. One of our standards is to prove that any point on the perpendicular bisector is equidistant from the two endpoints. So I'm going to say that I'm given that point J is a point on the perpendicular bisector of segment KL. Which means that KR is equal to RL and that RL is perpendicular to JR. And our goal is to prove that JK is equal to JL. In every proof, we start with the given. Now, one really important key to being successful in these triangle congruence problems is drawing on the diagram. You have to draw on the diagram as you do these problems, otherwise you can't see where to go next. So KR is congruent or equal to RL, and I'm given that KL is perpendicular to JR because it's given. Now these two triangles are touching, and so the reflexive property will be very useful for us in saying that JR is congruent to JR. Now, hopefully you can see that because they're perpendicular, that both of those angles must be equal because they're both 90 degrees. And now hopefully you can see that we have a side, an angle, and a side, and a side, and an angle, and a side. Now using the side, angle, side triangle congruence criteria, we know that these two triangles must be congruent. Because these triangles are congruent, I know all the corresponding sides and all the corresponding angles must be congruent. Specifically, JK must be equal or congruent to JL, meaning that point J is equidistant from point K and point L, which is what we were asked to prove in the standard. Go ahead and put a standard star next to that question, because proving that is one of our standards. In this video, we introduced the side, angle, side congruence criteria and used it to prove a couple of theorems, including two that are specifically mentioned in our standards. Thank you so much for watching.